Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an associate professor in the Department of Electrical and Electronics Engineering. In today's class, we are going to discuss about Faraday's law of electromagnetic induction, and this topic is from the module 4, and the module 4 is about the magnetic circuits. And in this module, we are going to discuss about the Faraday's law of electromagnetic induction, which means what are the various Faraday's laws and what exactly the Faraday's laws deals with, and now, what are the various principles are the laws that Faraday has proved, and also based on this Faraday's law of electromagnetic induction, we will also discuss about the various concepts like what is meant by the self-inductance and what is meant by the mutual inductance and what is the difference between the self and mutual inductance. Okay, and then after that we will also discuss the concepts called the dot conversion and coefficients of coupling and composite magnetic circuits, and finally we will discuss about the analysis of the series and parallel magnetic circuits. So these are the various topics that we are going to discuss in this module 4. So here all the topics are basically depends on the Faraday's law of electromagnetic induction. So that's why here it is very important to understand what is the Faraday's law of electromagnetic induction and actually what these laws deals with. So already we have seen, or we have discussed, discussed various laws associated with the electrical circuits, right? Especially the Ohm's law and Kirchhoff's current law, Kirchhoff's voltage law, like the various laws associated with the electrical circuits that we have discussed. And we haven't discussed about the magnetic circuits. Okay, so here to get understand, because here that we are going to discuss is about the electromagnetic induction or electromagnetic circuits of kind of. So which means it is the circuit is having the properties of magnetic circuits and as well as the electrical circuits. So that's why here I'm just trying to understand clearly. Okay, that's why here I'm just comparing the magnetic circuits and electrical circuits. What are the properties of the magnetic circuits and electric circuits? I'm trying to compare so that we will get understand clearly, okay, what exactly the magnetic circuits and what exactly the electrical circuits, and what are the difference between these two, and what are the common parameters or the common properties of these two that we can get understand. So first, a closed path of magnet. Of course, the magnetic flux will be also flow in a closed path. Once it is started at a point means then it will close at the same point. And similar like in the electric field, also a closed path of current. So here this is the magnetic flux and here it is the current. Okay. Then here the flux that we can define as our MMF by reluctance. So here MMF is nothing but magnetomotive force by reluctance, and here the current is nothing but, as we know, what is that, V by R. V is also called as a electromotive force. So here both are the forces, but one is magnetomotive force and another one is the electromotive force. So the magnetomotive force is we can get in the magnetic circuits, and the electromotive force that we can get in the electric circuits. Then here the reluctance means it is the opposition of it will oppose the flow of the magnetic field. Same like here the resistance. Okay, here the function of the resistance is it will oppose the flow of current. So similarly here the function of the reluctance here it means it will allow the field, the magnetic field, and the unit for the magnetic flux or field is, of course the field we can measure in terms of the flux. Okay, and the units for that flux is Weber, and here the flow of electrons is measured in terms of current, and the unit for this particular current, in terms of amperes we will measure the current. And the next point is the flux does not flow but sets up in a magnetic circuit. Okay, so which means of course it does not flow. Okay, it will set up in a magnetic circuit. So and here the current will flow through the circuit. Of course, the current will flow or passing through the circuit. And another point is here with respect to the MMF and EMF. So here MMF is the force because of which flux is set up in the magnetic circuits. Of course, because that's why it is a magnetomotive force. So it is a force because how this force will develop because of the because of the flux set up in the magnetic circuits. And EMF is the of course EMF is also a kind of force. When the EMF will set up, because of the EMF, okay, the current will flow through the circuit, right? Then of course that's what just now we heard is reluctance opposes the flow of flux, and here the resistance opposes the flow of current. So that is the difference between the reluctance and the resistance. And the flux density, which is phi by A, so flux by area. That's why here the units for the flux density is Webers per meter square. And here the flux density is represented by the capital V. And then when coming to the current density that we have already studied, that usually the current density is represented in J. So current, I by what is that again, the area of the conductor. So that's why here I by A, so which means A by ampere per meter square. A means here amperes. Then of course, the magnetic lines of force moves from always north to south pole. Okay, the magnetic lines of force will move from one pole to another pole, which means north to south pole. And electric current, we usually consider it will flow from high potential to low potential. That's why here move outwards for the positive charges, and move inwards for the negative charges. So that's why here high potential to low potential is nothing but, suppose let us consider here it is positive and here it is negative, then it will flow from here to here. This is high potential to low potential. So that's why from the positive it is away from the moves outwards, and from the positive, and move inwards for negative charges. So these are the some common properties are the the differences between the magnetic circuits and electric circuits. So now we got a basic idea how the magnetic circuit, what are the properties of the magnetic circuits and what are the properties of the electrical circuits, and what are the some key points related to the magnetic circuits, and the key points related to the electrical circuits. So then some more in detail about the magnetic circuits. So here a closed path followed by magnetic flux is known as the magnetic circuit. Right? A closed path followed by magnetic flux, okay, is known as the magnetic circuit. So which means here, as you can see here, this is the coil. Okay, in this coil here, of course, this is the what is that, flux. Okay, so here the magnetic flux. So here the magnetic flux. So the closed path followed by this magnetic flux, this is called as a magnetic circuit. This is called as a magnetic circuit. Then the strength of this magnetic or the flux, the strength of the magnetic field is measured in terms of the flux, and we know the units for the flux is Webers. So in a magnetic circuit, so the flux starts from one point and finish at the same point. So yeah, of course, because it is also a closed path. So that's what here. Suppose if you consider here the magnetic flux is starting from this point, then which means again it will flow through the circuit, and again it will end at the same point. So that is what here one more property of the magnetic circuit. So this is a similar to that electrical circuit. So even in the electrical current is also, it will start at one point and it will again end at the same point. Then a magnetic circuit usually consists of the magnetic materials having high permeability, right? So because of course we should have the magnetic material, the magnetic material, okay, the magnetic material property conductors, so then only it will produce the magnetic field or the flux. Okay, so the path followed by that flux, we can call it as a magnetic circuit. So some materials, some magnetic materials, those are having the high permeability are like iron, soft steel, etc. Okay, because they offer the small opposition to the magnetic flux, right? Okay, then the electrical current flows along a wire, creates a magnetic field. So of course, how generally the magnetic field is created. Okay, so whenever a current carrying conductor, whenever a current is flowing through a conductor, okay, or a coil, okay, then a magnetic field around the wire will be set up. Okay, and the magnetic field, okay, I mean, it can be visualized by showing the lines of the magnetic flux. Okay, so which means here the lines are called. We can represent the field in terms of the magnetic lines. Okay, so that is how the magnetic what is that field can be visualized. And of course, we usually it represented with a symbol of phi, which is nothing but the flux. Okay, so here the flux is used to measure the strength of the what is that magnetic field. Okay, same like in the electric field. Okay, so the current means, how the strength of the what is it, the flow of electrons. Okay, so or the rate of flow of electrons is nothing but the current. So how many electrons are flowing through a conductor in a second is called a current. So that's how there we measure the flow of electrons in terms of the current. So here we will measure the strength of the magnetic field in terms of the flux. Then the direction of that field can be, of course, here, because here there is a conductor, and in that conductor we are flowing, our conductor, that conductor carrying a coil. Okay, so the conductor, around the conductor we just placed a winding. So if you a current is flowing through that particular winding, then the magnetic field will set up so that the flux will develop. Okay, and the direction of the field or the flux can be determined by using the Fleming's right hand rule. So okay, that we will discuss later. What is Fleming's right hand rule, and by using that Fleming's right hand rule, so how you can measure, or how you can identify the direction of the field. Because here, of course, based on direction of the current, we can identify the direction of the field by using the Fleming's right hand rule. Now we understood the basic properties of the electrical circuits and the magnetic circuits and electromagnetic circuit also, because whenever a current is flowing through the coil, the magnetic field is set up around the coil, so which means there is an electrical current is there. So the current is nothing but the electric field is there, and flux is there, is nothing but the magnetic field is there. So that is electromagnetic circuit. We can also call it as an electromagnetic circuit. Yeah. Then coming to the Faraday's law of electromagnetic induction. So these Faraday's laws deals with the electromagnetic induction. So how the MMF will induced or EMF will induced in a circuit. Okay, and how to measure that the amount of the MMF induced in the circuit. So these Faraday's law deals with these things, right? So these electromagnetic induction was discovered independently by the two scientists. One is Michael Faraday in 1831 and Joseph Henry in 1832. But the Faraday was the first to publish the results of his experiments in 1931 on August 29. And he was an English physicist who gave one of the most basic law of electromagnetism. So that electromagnetism, is renamed as a Faraday's law of electromagnetic induction, because the electromagnetism is developed or defined by the scientist called Michael Faraday. So that's why here the law, the electromagnetic induction or the electromagnetism law is called as the Faraday's law of electromagnetic induction. So of course, at the first, this law was rejected because of the lack of the experimental proofs, and also some theoretical calculations related to the how much EMF is or MMF is produced by that magnetic field. Okay, so and that MMF produced by the magnetic field depends on which parameter. So that relation he could not prove. Okay, so that's why initially it was rejected, but after that he has done the experiment and he has developed the mathematical relation between the various parameters present in the electromagnetic circuit. So then of course, this law is very familiar, especially in the electrical utility, because the major applications are based on this law. Okay, which are the electrical motors. Okay, so all the electrical motors, irrespective of DC or AC, whatever it may be, so all electrical motors and generators worked on the Faraday's law of electromagnetic induction only. So not only electrical motors and generators, and the transformers also. So we can commonly we can call it as a electrical machines. Okay, so some are rotating machines and some are stationary machines. So the rotating machines are the electrical motors, generators, and the stationary machine is we can call it as the transformer. right? So because these what is the devices, okay, the electrical motors, generators, and transformer basically works on the principle of electromagnetic induction only. Then the Faraday's law of electromagnetic induction, okay, is the basic law for the electromagnetism, predicting how the magnetic field will interact with an electric circuit to produce the EMF, right? So I mean, which means he developed a relation between the magnetic and electric circuit, okay, and by the combinedly how an EMF, which is the electromotive, will produce in that circuit that he will explain. And this phenomenon is also called as electromagnetic induction. Of course, we know because this we have already discussed in electrical. Not discussed. I mean, we will discuss in or we will discuss detailed in when we are discussing about the principle of operation of the electrical machines, which means motor and generator, right? So then the Faraday's law states that a current will be induced in a conductor which is exposed to a charging magnetic field, which means, because as you can see, so let me give you a simple difference between, or the better understanding of this Faraday's law of electromagnetic induction. So first let us consider an electric motor principle. Okay, let us consider a DC motor principle. So here we know already the function of the motor is it can convert the electrical energy into mechanical energy, and similarly when coming to the generator, so it will convert the mechanical energy into electrical energy. So in both the cases here, let us consider here the mechanical energy is nothing but the rotating energy. Okay, that rotor or the coil, the rotating. So that is called as a mechanical energy, and whatever the current is flowing through that particular coil or EMF used in that coil, we can call it as a electrical energy. So first let us go with a generator principle. So because here the Faraday's law states that current will induced in a conductor, okay, which is exposed to the changing magnetic field, right? Okay, so which means suppose if you, the function of the generator is mechanical energy to electrical energy. So when you place a rotating coil in a magnetic field, okay, rotating coil in a magnetic field, then an EMF is induced in that coil, because that the coil is rotating in the magnetic field. It changes the field, okay, or it cuts the magnetic flux, okay, so that an EMF is induced in that coil. So that EMF induced in that coil, because if you close that circuit, then the current is also flowing through that coil, so that we are getting the electrical energy. So the rotation of the coil is the mechanical energy, and when you are placing a rotating coil in a magnetic field, then the current is, or the EMF is induced in that coil. Okay, if you close that circuit, then the current is also flowing through that coil, so that is called the electrical energy, right? So which means how the current is, or the EMF is induced in that particular coil because of the magnetic field. Okay, because of the magnetic field. So that is how the relation between the electrical and magnetic field, right? Then according to the Lenz law, okay, so according to the Lenz law, the electromagnetic induction states that the direction of the induced EMF will be such that the magnetic field created by the induced current opposes the initial change in the magnetic field. Okay, which means whatever the current produced in that field is opposing to the change in the magnetic field. Okay, so which is states that the Lenz law. So in next slide we will discuss in detail about the Lenz law. Then the Faraday's law of electromagnetic induction explains the working principle of transformer, motor, or generator, and inductors. That's what just now I have explained. So when coming to the motor principle, so motor is electrical energy to mechanical energy. So whenever a current carrying coil placed in a magnetic field and an MMF is produced, okay, that means the force, okay. So it will, the force, okay, because of that force, the coil will rotate. So which means whenever a current carrying coil is placed in a magnetic field, it experiences a force to rotate. So that rotating energy is called as mechanical energy. So which means electrical to mechanical. That is how these motor and generator will work based on this electromagnetic induction principle. So which is also called as the Faraday's law of electromagnetic induction. Then there are two Faraday's law of electromagnetic inductions are there. So the first law of electromagnetic induction consisting, the first law describes the induction of the EMF in a conductor. So which means how the EMF is induced in a conductor. And the second law is related to quantify the EMF produced in the conductor. How amount of the EMF is induced in that conductor, and how to evaluate the amount. I mean, the amount of the EMF is induced in that conductor or the coil. So these are the two Faraday's law of electromagnetic inductions. So first, let us discuss about the Faraday's first law of electromagnetic induction. So according to this Faraday first law of electromagnetic induction, so of course, it is carried out based on some long series of experiments. Okay, so finally, I mean, the experiment was success, so that everybody is approved that Faraday's law of electromagnetic induction. Okay, so from this experimental observation, what the Faraday is observed, or what the Faraday concluded, an EMF is induced in a coil when the magnetic flux across the coil changes with time. Okay, so an EMF is induced in the coil. Okay, when the magnetic flux across the coil changes with time, right? So which means any one of the field must be changed. Either it should be the magnetic field or it should be the electric field. Then only an EMF is induced in that coil. Okay, because anyway here, of course, the coil. Let us consider here the coil is stationary, and the magnetic flux across that coil is changes with respect to the time. Then EMF is induced in that coil. If you observe this particular circuit, okay, so here initially, what is that? This is at a zero position. So whenever the coil is moving towards whenever the magnet is moving towards the coil, which means here the change in the magnetic field is happening. So because of that, and current is flowing through that particular circuit. Okay, so that is what the Faraday's law of electromagnetic induction. That is what the first Faraday's law of electromagnetic induction. So which means whenever a conductor is placed in a varying magnetic field, okay. So whenever a conductor is placed in a varying magnetic field, an EMF is induced in that coil. Okay. So if the conductor circuit is closed, then the current also will flow through the particular circuit. So that is how the mechanical energy is converted into electrical energy, or that is how the EMF will be produced by the magnetic field. Right. So here it is very clear and very simple. Okay. So whenever a conductor is placed in a varying magnetic field, then an EMF is induced in that coil, and if the coil is a closed circuit, then the current flowing through that coil. So that is what the Faraday's law of electromagnetic induction. And here from this circuit you can clearly observe. Okay, so in the first case, in the figure A, there is a coil, and here of course you are moving this magnet towards the coil. Okay, which means of course there is a change in the magnetic field. So because of the change in the magnetic field, here you will get a current. Okay, so which means an EMF is induced in that coil, and if you close that coil circuit, then the current will flow through that coil. And in the second case, okay, in the figure B, okay, if the coil is stationary, okay, you are not moving, which means here the magnetic field is also stationary, so it is not changing with respect to the time. So that's why here there is no EMF is induced in that coil. Okay, so that here even the current flowing through that coil is also zero. And in the third case, as you can see here, again the coil, okay, sorry, not coil, here the magnetic bar is moving away from the coil. Okay, so here it doesn't matter whether you are moving the magnet towards the coil or away from the coil. Okay, so it is the matter of whether you are moving the coil or not. Sorry, whether you are moving the magnet or not. Because if you are moving the magnet, then only the magnetic field or the flux will change with respect to the time. Otherwise, there is no change in magnetic field or varying magnetic field. Okay, so because according to the Faraday's first law, when a current carrying coil is placed in a changing magnetic field or varying magnetic field, then only the EMF is induced in that coil. Otherwise, there is no EMF induced in that coil. So if there is no EMF induced in that coil, then there is no current flowing through that particular coil. Okay, so that is why here, even though if you are moving towards the coil or away from the coil, okay, so there will be a EMF induced in that coil, and because of that the current is flowing through that coil. But here in case B, the coil is the magnet is stationary, so which means field is stationary, so that's why here there is no current flowing through that coil. And here of course in the case D, okay, in this figure here still the magnet is stationary, but the coil is moving towards the magnet. So which means again, because of the coil moving towards the stationary magnet, again the flux, the field linking with this coil will change. so that an EMF is induced in that coil, so that the current will flow into that coil, right? Okay, so of course here the flow of current is depends on, okay, the direction of the the field, right? Whether you are moving towards the coil or whether you are moving away from the coil. So based on that, here the current direction will changes. Okay, so because as you can see here, this is current flows, and here the current flows oppose the way, because before here it is flowing some, let us consider in this way, now it is flowing in this way. So that is what the direction of the current is also depends on the direction of the field. Okay, the direction of the magnetic field. So which means from these various figures that we can conclude. So when the magnetic, the EMF will induced in that coil, okay, according to the Faraday's law of electromagnetic induction. So here these are the a few points that we can observe. Okay, which means a few ways to change the magnetic field intensity in a closed path. Okay, because if you are able to change the magnetic field intensity, then only we will get the EMF induced in that coil. So the first one is by rotating the coil relative to the magnet. Okay, so which means the magnet is stationary and the coil is rotating. So in that case also an EMF is induced in that coil, right? In the second case, by moving the coil into or out of the magnetic field. So which means here you no need to rotate. Okay, just if there is a movement, okay, either it is a linear movement or the angular movement. So it doesn't matter, but either the coil should be moved or the magnet should move. Okay, then only there will be a change in the magnetic field or the flux with respect to the time, so that an EMF is induced in that field. So, and the third case, by changing the area of the coil placed in the magnetic field. Okay, by changing the area of the coil placed in the magnetic field, in that case also, which means there will be the change in the magnetic field, so that the EMF is induced in that coil. And by moving a magnet towards or away from the coil. So as you can see here, by using this point and this point, if you observe, here the coil is moving, okay, into and out of the magnetic circuits, and here the magnet is moving towards and away from the coil. So in the both the cases, you are getting the EMF. Okay, so that's what here the point is. Here there is no compulsory that the coil must be moved, or there is no compulsory that the magnet must be moved. Okay, so any one of the coil or the magnet should be move, okay, or displaced. Okay, either they are rotating or just moving towards or away from the particular the coil or the magnet, so that an EMF is induced in that particular circuit. Okay, so this is how about the Faraday's law of electromagnetic induction. So I hope everybody clear about how what the Faraday's law, first law deals with, and according to Faraday's law, first law, how an EMF is induced in that coil. Okay, so the process of EMF induced in the coil is called the Faraday's law of electromagnetic induction, right? Then the Faraday's second law of electromagnetic induction. So this second law deals with of course an EMF is induced according to the first law, but what is the amount of EMF? Okay, how to quantify that EMF induced in that coil? So okay, that relation is developed, or that relation developed based on the Faraday's law of second law. So here the Faraday's law of second law of, or the Faraday's second law of electromagnetic induction states that an induced EMF in a coil is equal to the rate of change of flux linkage with the coil. Okay, an induced EMF in a coil is equal to the rate of change of flux. Okay, and the flux is we know already, the flux is the product of number of turns in a coil and the flux associated with that coil. Okay, so that is mean by the flux. Okay, so that's why here the epsilon, it is called as electromotive force, so, or the EMF is equal to minus n into delta phi by delta t. So here why minus n? Because according to the Lenz law, okay, so the EMF induced in that coil is opposite to the direction of the force. So that's why here E epsilon is equal to minus n into d phi by dt or delta phi by delta t, because here delta phi is changing flux with respect to the time, right? Here n is the number of turns of the particular coil. Yeah, then here the Lenz law. So a German physicist Lenz, he define a rule known as Lenz law. Okay, that describes the polarity of the induced EMF. Okay, the polarities of the induced EMF, because the Lenz law states that the polarity of the induced EMF is such that it tends to produce a current which opposes the change in the magnetic flux that produced it. Okay, so that's why in the previous case here we placed a negative sign. So EMF, the EMF induced are the electromotive force which is equal to minus N into delta phi by dt. And the negative sign of the formula represents because of the Lenz law effect here we are representing it as a negative sign. Then the derivation, okay, how we can derive that, what is it, the Faraday's law of second law, the derivation, okay, so that is EMF is equal to how minus N into d phi by dt. So from this here you can see, let us consider the flux linkage with the coil at the time of t1, because there is a change in flux, then only you will get the EMF is induced in the coil. So that's why with respect to t time. So the flux linkage with the coil at an instant of time t1, which is equal, let us consider N into phi 1, because the flux is equal to the total flux linkage to the coil is equal to the number of turns into the flux associated with that particular coil. So that's why let us consider here N is equal to number of turns. And then the flux linkage with the coil at the instant of time t2, which is t2 is equal to N into phi 2, then the change in the flux linking by that coil is equal to N into phi 2 minus phi 1. Okay, and let us consider the change in the flux linkage as, okay, I mean, because in both the cases the number of turns are same, so that's why let us consider. So here the change in the flux phi is equal to phi 2 minus phi 1, so that this equation will become N into phi. So here N into phi is the change in flux linkage with the particular coil. And then the rate of change of flux E, here it is N into phi by T. Okay. So, and by taking the derivation for the above equation, then we can write it as N into d phi by dt. So, according to Faraday's second law here, the electromagnetic induction, which is equal to the rate of change of flux. Okay. So here just now we have derived the rate of change of flux E is equal to N into d phi by dt. But by considering the Lenz law, we should keep the negative sign. So which means here from this equation we can see that increase in the number of turns. Okay, increase in the number of turns of the coil also will increase the the EMF or the induced EMF in that particular coil, and increase in the magnetic field strength, which means here increasing the flux is also is caused to increase the induced EMF in the coil, and increasing the speed of relative motion between the coil and magnet, okay, will also affect the change in the induced EMF. Okay, so this is how about the Faraday's law, first law and second law, right? And next about the concept of the self-inductance and mutual inductance. So this we will discuss in the next class. Okay, what is the concept of self-inductance and mutual inductance? So what is mean by the self-inductance and what is mean by the mutual inductance? Okay, so where we use the self-inductance and where we use the mutual inductance, these things we will discuss in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.